Good morning. We will start third session on chapter Force and Laws of Motion. In our previous session, we studied about Newton's first law of motion, which is based on inertia, wherein we also call that as law of inertia. So we understood about inertia of rest, inertia of motion, few applications from our day-to-day life examples. So today we will start with Newton's second law of motion. To understand Newton's second law of motion, we need to first understand the term momentum. So what is momentum? We define momentum as the power of motion of an object. That means how fast the object can travel. That means we talk about its velocity, right? We talk about power of motion. The object can travel, that is the motion of an object with respect to its velocity, right? But when the object is traveling, there is another thing which is more important. Now again, if I give you an example, if I have a heavy carton box and if I have a very light carton box, right, and I apply equal velocity, the object is moving with some velocity, which will move with a faster velocity? Of course, the object with a lighter mass, correct? That means when we calculate the power of motion of an object, we should know with what velocity it is moving. Depending on the velocity, what is the mass of an object, right? So we define momentum as the product of mass into velocity. Momentum is written as italics letter P, mass into velocity. SI unit is for mass, it is kg. For velocity, it is meters per second. So SI unit of momentum is kg meters per second. Now still in better terms, if you have to understand momentum is, suppose a bullet is fired from the gun. Okay. So when the bullet is fired from the gun, the mass of the bullet is very negligible. It has a very small mass. But with what velocity the bullet is moving can actually pierce a log of wood, can actually kill a human being, right? Now, for example, there's a person who is firing the bullet from the gun, and assume that there is another person who is just throwing the same bullet from the hand. So do you think the one who is throwing the bullet from the hand can pierce a log of wood? No, because we need to also know with what velocity it is traveling. That means along with mass, velocity also plays a very important role to calculate the power of motion of an object. That is, momentum is nothing but product of mass into velocity. Now another example, like suppose we are going on a two-wheeler or a four-wheeler with a very slow speed. Somebody comes and hits us. Chances of we fall down, but chances of getting hurt is less, right? In the another case, suppose if we are going in a very high speed and somebody just comes and dashes or hits us, that means we are heavily injured. That means it depends upon the velocity. Suppose you go and hit a moving bus, you get hurt very badly, right? You go and hit a standing bus, the chances are less of getting hurt. That means as the body is in motion, moving with a greater velocity, the momentum of that also increases. Now momentum of a bullet is more than the momentum of a bullet where I am hitting it with a hand, rather it is fired from a gun. So momentum is nothing but mass into velocity. Now another example what I have to give you here is, now this was again proved by Galileo. So what he told was, suppose if I throw a feather and a ball together. Now of course, feather and ball have different mass, right? But they are going or they are dropping or we are throwing them with the same velocity. Which will reach the ground first? Okay. Of course, anybody can answer, since feather being a very lightweight, the ball reaches the ground first. But in case, let us assume that Galileo's assumption in a frictionless path, or if there is no air resistance, if there is no disturbance or no external force. Here air plays an external force here, right? Assume that there is no air and this is done in the vacuum, right? We throw a feather and we throw a ball having different masses but with the same velocity. Surprisingly, you will notice that the ball and the feather comes down to the ground at the same time. Yes, because there is no air resistance. There is no anything which is opposing. So an object, if it is in moving, it continuously starts to be in the motion because there is nobody to disturb the object. That is what the Galileo's assumption was, right? But again here if I ask you, which is very easy to catch? Feather or a ball? Of course, feather is very easy to catch because it has a lighter mass than the ball. So this is about the momentum. Few just examples about the momentum. We have many numericals on this part momentum which we will be solving in our regular classes. Now, Newton's second law of motion is based on momentum. That is why we understood the concept of momentum first. What does second law tell us? Rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. That is, it tells us the rate of change of momentum is directly proportional to whatever force is applied on the given object. We are supposed to prove this second law statement mathematically, a very important derivation. It is usually asked, derive Newton's second law of motion mathematically, right? So, in today's class, what we will do now is, as we understood what is momentum, based on the momentum, we understood how Newton's second law is based on momentum. We will understand the mathematical derivation of second law of motion, and in our next session, we will understand the applications of Newton's second law of motion and law of conservation of momentum. Now let us derive Newton's second law of motion mathematically. So now we'll understand mathematical expression for Newton's second law of motion, a very important derivation which can be asked for 3 marks. So let us assume that let mass of an object be m kg, or we can assume that let an object starts moving with mass m with initial velocity that is u meters per second and final velocity v meters per second. Initial momentum of an object is given by, this is momentum is given by m into v, that is product of mass into velocity. Since it is an initial momentum, we take m into u. Final momentum of an object is given by m into v. Change in momentum is given by final momentum minus initial momentum. That is nothing but mv minus mu. So I can take m common, v minus u. So rate of change of momentum. We always know that rate is always with respect to time. So rate of change of momentum is given by change in momentum upon time. So that is nothing but m of v minus u upon t. From Newton's second law, or according to second law, we know that rate of change of momentum is directly proportional to force. Yes, that was a derivation of, or that was a statement of the second law. So I'll write here, force is directly proportional to rate of change of momentum, written here. What is v minus u by t? If you recall in the motion chapter, equations of motion, acceleration, how did we derive it? A is equal to, or acceleration is equal to final velocity minus initial velocity upon time. So we have the same thing here, v minus u by t. So can I substitute the value of acceleration as v minus u by t? Yes. So force is directly proportional to mass into acceleration. Whenever we have to remove the proportionality symbol, we take one term as constant. We have taken F is equal to K as a constant into mass into acceleration, where K is the constant of proportionality whose value is assumed to be 1. Now why did I choose K? I could have chosen X. Yes. I could have chosen Y. Yes, I could have chosen any alphabet, right? So we usually choose some common alphabets in the derivation. So we have used the word k here, where k is the constant of proportionality whose value is assumed to be 1. Therefore, F is equal to ma. This is what the first we derived when we understood what is force is also defined as a product of mass into acceleration. So this is the derivation for second law of motion. Now based on this derivation, we will also define, now what is SI unit of force? Newton, right? So we will be defining what is 1 Newton in our next class. We will also learn few basic applications or day-to-day life examples based on second law of motion, as well as we will derive an equation for law of conservation of momentum. So in today's class about momentum, Newton's second law of motion and its mathematical derivation, if you have any doubt, you can call on the same day of the video set.